Good morning, all of you. Welcome back in your online lecture series for the topic Nanoscience and Technology. We are discussing the introductory part of Nanoscience and Technology. Myself, Dr. Harale, Assistant Professor, Department of Physics, S.G.M College, Karak. I am discussing the introductory part of Nanoscience. This is our fourth lecture. So, we will discuss more regarding Nanoscience and Technology. Up to now, we have discussed various parts of nanoscience and technology. What is meant by nanoscience? What is meant by technology? What is meant by nanotechnology? Various parts, aspects we have already discussed. In our last lectures, we have discussed regarding milestones in nanotechnology. What are the milestones? How is the nanotechnology developed up to now? Historical development in milestones in the development of quantum mechanics. How the quantum mechanics develops. From ancient times to up to now, what are the different development take place in quantum mechanics. Now, dimension dependent classification of nanomaterials we have already discussed, and size dependent, what are the different properties which are the size. So, in case of nanomaterials, the size and shape, these are the very important. So, there are size dependent and shape dependent properties we have already discussed in our last lecture. Now, what the basic for this responsible for this nanoscience and technology, what is the theoretical aspects related to that nanoscience and technology we are going to discuss regarding the same. What happens at the nanometric scale? So we know the any materials or matter made up of atom. When various atoms comes together, a group of atoms, small 1, 2, 3 number, some group of atoms comes together which forms the molecules. Some molecules comes together from the clusters, which is also sometimes known as molecular cluster, and from this cluster there is a formation of crystalline. If there is some limited number of atoms or limited number of molecules which form the crystallites, which is known as nanocrystallites. So just basic is that here cluster, formation of cluster may be in terms of gas cluster, semiconductor cluster or metallic cluster. In case of gas cluster, so inert gas are weakly held together by van der Waals force. How they are get together, held together by van der Waals interactions. For example, helium gas. In case of semiconductor clusters, they are held with strong directional covalent bonds. For example, silicon cluster. In case of metallic cluster, they are fairly strongly held together by delocalized non-directional bonding. For example, sodium. So this is a fundamental concept of atom molecule cluster and formation of nanocrystallites. So we are dealing with that nanometrics. What is nanotechnology? Nanotechnology is manipulation at the atomic or molecular level, manipulation of matter at the atomic or molecular level. So we have to discuss, we have to study what happens at atomic level or molecular level. So for the description, in case of microsystem, we are dealing with classical mechanics, but when we are consider the atomic and molecular scale, the classical mechanics does not sufficient to describes the atomic and molecular behavior. That's why we have to go for quantum mechanics. So at the nanometric scale, there is one effect which is called as quantum confinement effect. In case of normal atoms, they are brought together in the bulk material, the number of energy state increases substantially to form a nearly continuous bands. Here we can see the continuous bands of state. 1 atom, 2 atom, 3 atom, 4 atoms comes together. Each atom possesses its own energy levels. When they comes together, which forms a mixing of energy levels, which forms like a continuous bands. So each energy level has its own energy, but when they comes together, it looks like a band, continuous band structure. How we can distinguish between that bands? Here from this figure you can understand easily. In this figure, in case of metal, the conduction band and valence band merge together. That's why there is no any gap between that valence band and conduction band generally. So these are the band band structure for this metal. In case of semiconductor, there is a small difference which is called as forbidden gap. So conduction band and valence band is separated with some forbidden gap, and that energy required to overcome this gap, which is called as band gap energy. So here is the conduction band of semiconductor, and here is the valence band of semiconductor. When you go at nanoparticle level, what we observe that this bands, conduction band and valence band energy level get not in continuous form, but they get separated and it's discrete form. So you can observe here the lines in discrete form. Again you go for cluster level, that is you are going from bulk to nanometric level, nanoparticle level, then cluster level. Again you will find the difference between that is increases. So here you can observe the difference between conduction band and valence band is here a smaller one. In case of nanoparticles, the band gap is higher. Again you go for cluster, then again you will find that band gap, the gap between that conduction band and valence band, you will find that increase. Again you go with the molecular level, the gap between that HOMO level and LUMO level, you will find the much more than the cluster. And when you go for atomic level, you will find the more difference, clear cut discrete lines in case of atomic scale. So that's the phenomena or effect which is called as quantum effect. So why this happens, why this quantization effect take place at nanometric scale? Because in the case of nanometers, maybe one dimensional, two dimensional, three dimensional, one or more dimensions are restricted, means the movement of carriers are restricted in a particular direction. That's why this phenomena is called as quantization. Quantization, what is quantum? Quantum means quantum energy, quantum, and its confinement. Confinement means restriction. So quantum confinement effect is restrictions on the carriers in that particular nanometric level. So here we can understand what happens at nanometric level. The quantum confinement is a special confinement of the electron hole pairs, which is exons, in one or more dimension within that material. So material may be one dimensional, two dimensional, three dimensional. This is a nanometric level. So quantum confinement effect is observed when the size of particle is too small, very small size of that particle compared to the de Broglie wavelength. And then this effect, we can break this word like quantum and confinement. Here confinement means the confine the motion of randomly moving electrons in that to restrict its motion in specific energy levels, means you are moving from continuous energy levels to the discrete. So discrete energy levels. This quantum reflects the atom realm of the particles. So as the size of particle decreases till we reach a nanoscale, the decrease in the confining dimension makes the energy level discrete, more and more discrete, and this increase the widen up the band gap, and ultimately the band gap energy also increases. So this you can consider in case of bulk. Here is the conduction band, here is the valence band, here is the band gap energy. And when you go at the nanometric scale, or with respect to or in case of nanomaterials, at the nanometric scale, you will find this energy level get split into different discrete energy levels, and you observe here the band gap is increased in case of nanometric scale. So what happens at that level? Now what is quantum dot size and relation of quantum dot size with band gap? What happens with that size dependent on how the band gap changes with the size of that quantum dot. Quantum dot is nothing but is an example of zero-dimensional nanomaterials. The band gap of spherical quantum dot is increased from its bulk value by the factor of 1 by r square. What is r? R is a particle radius, or you can call it as size of that. You can call it as 2r equal to the diameter or size of that particle. Now, what does this means? These quantum dots are band gap tunable size. When you change the size of that quantum dot is again nothing but zero-dimensional nanomaterials. Band gap tunable by size. When you change the size of that, there is change in energy level, discreteness increases, and we can engineer their optical and electrical properties. Now, smaller the quantum dots have the larger band gap. When you decrease the size more and more, less you decrease the size lesser and lesser, you will find the more and more splitting, and there is an increase in the band gap. So absorbance and luminescence spectrum are blue shifted with decreasing particle size. When you decrease the particle size, you will find out there is a blue shift. So here is a color of that is red, then shifting towards green color and shifting towards blue colors. Here you can observe easily the band gap increases. So this is nothing but the increase in the band gap of material when decreasing the size, which is a simple quantum confinement effect. From band structure we can easily understand. Here we have already discussed a bulk band structure, and in case of bulk material, here is a conduction band, here is valence band, and you will find the bands are not in discrete state, they are in continuous state, and their conduction band and valence band separated with a finite gap, which is band gap. In case of quantum size, or in case of quantum dots or nanomaterial at a very smaller size, you will find that again there is a splitting of energy levels and increase in the band gap, and respectively when the decreasing the size, you can find out the blue shift. So emitting color or output color of that quantum dot is, here is a red, then again here is a green color, and here is a blue color. So that's the quantum confinement effect, in which the band gap increases when you with the decreasing the size of that nanoparticle quantum dot. This is an example of a quantum dot. When you eliminate the quantum dot with UV light, you will find the different colors. Why this appears the different color for the same material of quantum dot? Because due to the change in size. In red color there is a higher size, and when you decrease the size, you will find the change in color. Now this is nanotechnology is not started in a few days ago or few years ago. It started long back in ancient times. In a famous example is Lyra's curve. In what happens with Lyra's curve, that when you eliminate this curve from the front side, you will find out this appearance like some part green color appearance. When you eliminate this curve, like this curve from back side, you will find its appearance is red. So that's the nothing but use of that silver and gold nanoparticles embedded in that glass. That's why this changing its optical properties. So in reflected light, the curve appears green. In transmitted light, it appears red. So this is the same glass, but when you eliminate the light from front side or back side, you will find out a different appearance or different color, which is here is a green and here is a red. Why happens this? Because they embedded with the 70 nanometer particles of silver and gold in the glass. This is the beauty of that nanomaterials, nanometric scale materials they have used in ancient times. Also same type of polychrome luster were bound. So poly means a different colors, appears in different colors, same material with appears in different color. In churches, the windows you will find the painted with using the gold nanomaterials, having the different colors, appearance different. So that's the this nanotechnology or nanomaterials they are using from ancient times, but we don't know at that time. They are not aware that they are dealing with that nanotechnology. In 13th to 18th centuries, here the Damascus saber blades, you will find out it has extraordinary mechanical property. It has a greater strength. When this blade is dissolved in hydrochloric acid, a smaller part of that, and tested under the high resolution transmission electron microscope, you will find out these presence of carbon nanotubes. carbon nanotubes, it has a higher tensile strength, mechanical properties as compared to the normal screen, normal steel. At that time, they have embedded this carbon nanotube in that blades. That's why it possesses extraordinary mechanical properties. So from this examples, we can realize that this nanotechnology is far years ago the people have started already using that nanotechnology. So what is the history of that? So in 1965, Jordan Moore described the electronic magazine several trends in the field of electronics. One trend, which known as a Moore's law, it described the density of transistor on an integrated chip, IC chip, doubling every 12 minutes. The basic trend Moore envisaged has continued for last 50 years to a large extent as ICs and transistors have approached nanometric or nanoscale dimension. So in 1974, the word nanotechnology, this term is coined by the Nario Taniguchi. He is a scientist, Japanese scientist from University of Tokyo. It's a production technology to get ultra fine accuracy and precision of 1 nanometer. So he is the first scientist who gave this term nanotechnology. In 1981, IBM invented S.G.M, standing tunneling microscope, which can move a single atom around. So this is a development in nanoscience and technology. In 1985, few form of carbon discovered C60, which is a full ring C60 carbon atom arranged in a sphere made up of 12 pentagons and 20 hexagons. This is structure discovered in 1985. So before that, in 1857, Michael Faraday, who discovered the colloidal ruby gold, demonstrating that nanostructured gold under a certain lighting condition produces a different color solution in 1857, long years back ago. In 1959, Richard Feynman, we have already known, there is a plenty of rooms at the bottom who gives this nanovisionary concept. In 1991, carbon nanotube discovered by scientist S.G.M, graphite carbon needles ranging from the 4 to 30 nanometer and up to 1 micron in length. So he got the new Nobel Prize for that, S.G.M, the Japanese scientist. In 1993, the first high quality quantum dots prepared very small particles with the controlled diameters of CDS, CDT and CDSE. In 1993, the first high quality quantum dots prepared. In 2000, first DNA motor made similar to motorized tweezers may make a computer 100 times more powerful, and this reports published in the Nature. So DNA motors can attach to electrically conducting molecules which act as a basic switches. In 2001, a prototype fuel cell made with a nanotube using the different nanotubes. In 2001, prototype fuel cell prepared. 2002, Nanomaterials make a strain repellent trousers. They have used in nanomaterials in textile industries and make a strain repellent trouser by using that nanomaterials. So we have discussed regarding brief history of that nano science and nanotechnology, and we are using the direct nanotechnology in day to day life. These are the various examples in which the nanotechnology is directly used, like various companies like Mercedes company and other like Kodak company, Samsung company. They are using this nanotechnology for their product in automobile sector or in electronic sector, in the smart windows and solar cells, different areas. Already the company started using this technology and preparing their own products. So these are some logos some companies, especially very large manufacturers, has some form of nanotechnology initiative. They have taken the initiative to fabricate devices or product by using that nanotechnology, like a famous company BMW in automobile sectors, Nokia company in electronics, Samsung company, so many Philips company, so many companies are there already started to use this nanotechnology. So here some reports are available with this by use of this nanotechnology in different sectors. So for that, ultra fast data storage in automobile sectors, or in detecting and diagnosis of this cancer, or any other biomedicine or medical field, to control the pollution, to make a sustainable way for the green energy by using nanomaterials. Different for the space applications, people's already NASA has already started using this nanotechnology for space application. And here nano coatings for these various applications, sports or sensors, like that various applications the nanotechnology already started to use. Just a simple example is Michael Phelps, who got these various medals, got 8 gold medals. So look here, the suit of the swimming suit of this Michael Phelps. Here you can find out this suit is made up of using nanomaterials. That's why he is not swimming in the water, but like us floating on the water. That's why the resistance between that suit and this water is very less. That's why the speed of his swimming speed is increased, and he got help of this suit to win this gold medals. These are some energies, different sectors like energy, medicine, nano, biotechnology, nano devices, optical engineering, defense and security, bioengineering, cosmetics, nanofabrics. These are the various fields in which we can use this nanotechnology. So details regarding that part, regarding various applications of nanoscience and technology, we will discuss in our next lecture. Thank you.